Hi guys, and welcome to our next unit on thermochemistry. All right, thermochemistry is the study of energy changes that can occur during chemical reactions or even changes of state, and we're going to be talking about both of those. All right, how we get energy from chemical reactions is through what's known as chemical potential energy. It's the energy stored in chemical bonds. All right. While energy is kind of the overall term, sometimes we use the word heat instead of just energy. Heat is abbreviated with a lowercase q. All right. And when we're talking about heat, we're specifically talking about energy that is being transformed from one object to another. So when you touch a hot pan, that is the energy being transferred from the pan to your hand, and that is considered heat. All right, there's two major units for measuring heat flow, okay? One is going to be one that you're certainly familiar with, and that is the calorie. All right, the calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius, okay? If you notice here, I have a lowercase c, all right, because when we talk about calories, we're typically talking about the calories in food. And if you check any food label, you will notice that the word calorie there in the United States is a capital C. That capital C actually stands for kilocalorie. But we know in the USA, we don't really love using the metric system, so instead they use this capital C to talk about the amount of calories. All right. A true scientific calorie is actually a pretty small unit. All right. So that's why when you look at a food product and it tells you that it has 500 calories, that's actually 500,000 calories. All right. But nobody likes thinking of eating that much stuff, so they went with this capital C. Okay. So the SI unit for energy is the joule. 1 calorie, lowercase c, is equal to 4.184 joules, all right? This is gonna be one that certainly does come up as we go through this unit. Today, we're gonna focus on something that is called the specific heat capacity. And that is the amount of heat or the amount of energy needed to raise the temperature of 1 gram of a substance 1 degree Celsius, all right? Specific heat gets the abbreviation of capital C, lowercase p, and that stands for the specific heat capacity. The specific heat equation that we are going to be using, all right, that we're going to be using in this unit is often called the MCAT equation, and I'm going to show you why. So it's going to be your amount of heat is equal to the mass of your sample, all right, times the specific heat of that sample, times the change in temperature of that sample. All right, you'll notice through your notes and on here, I'm not very good at making these triangles, so they are supposed to be a triangle representing delta. Delta T means the change in temp. M is your mass, specifically in grams. All right, great. So let's keep going. Okay. So let's look at our first example here, remembering what our equation is. All right, so remember Q, heat, is equal to your mass times your delta T, all right, times your specific heat. How much energy, now remember when they ask for energy and heat at this point are interchangeable, so you're looking for Q. So how much energy is given off when 25 grams of water is cooled from 99 to 36? Okay, great. So we're gonna go Q, that's what we're looking for. What's my mass? It's 25 grams. All right, what is my delta T? Well, I want my delta T, make sure that's always a positive number. All right, so make a positive number. It's gonna make your life a lot easier. Okay, so 99 minus 36 degrees Celsius times your specific heat of water. And the specific heat of water, remember, all right, so the CP of water, we're gonna use 4.18, and that's in joules per gram times degrees Celsius. So here we go, 4.18 joules per grams times degrees Celsius. Now, before we put any of the numbers in, check your units and make sure they're working out. I have grams up here in the numerator and grams in the denominator from the specific heat. That divides out. This is going to end up being in degrees Celsius. All right, degrees Celsius. So that divides out. I'm just left with joules. I'm looking for energy, so that makes sense. That's great. So when I do this, I'm going to end up with Q, and that's an ugly Q, but that's okay. Okay, is going to equal, your calculator will give you something like 6,589. We're just going to be good and round that to about 6,600 joules, and that is your answer. All right, you have another question, number 2. Go on ahead and you can pause this video and go on ahead and answer that if you would like. All right, so let's look at number 2. When 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85 degrees. What is the specific heat for the olive oil? All right, well, again, we're using the same equation, except for this time we're going to be looking for specific heat. You know the amount of energy. I told you that it's 435. You know the mass. You know the delta T. So we're going to plug in all of those numbers. And you're going to get a specific heat of, I believe your calculator is going to give you something like 1.999, that type of thing. So 2.0 joules over grams times degrees Celsius. All right, just make sure that's in camera and then you can see what your final answer is for that one. Okay, fantastic. All right, so next up, what happens when you mix two things? And what I mean by that is what's going to happen when you take something hot, let's assume hot water, and you mix it with really cold water. Well, that may seem like a silly question, but if you should be able to answer that. You're going to end up, if you add something hot to something cold, you're going to end up with something warm, right? Something in between. Well, our job is going to be to figure out what that in between is going to be. So we call these heat gained is equal to heat lost problems. And what we're going to do for these particular problems, all right, is we're going to set up two specific heat equations and set them equal to each other. So let's take a look at our question here. All right, and this is question number 3. 150 grams of water at 75 degrees Celsius is mixed with 200 grams of water at 30 degrees. What is the final temperature of the system? All right, so we have water that's at 75 and water that's at 30. We know that our final temp is going to be somewhere between 75 and 30. And like I've always said, we love questions where there's an automatic check in them. So you know your answer must be between 75 degrees and 30 degrees Celsius. So let's go ahead and figure this out. All right, so my heat gained is equal to heat lost. So I'm going to set up my specific heat equations and set them equal to each other. So you're not actually looking for Q, all right? Whatever heat was gained by the colder substance, all right, it's because the hotter substance lost it. So we can actually do this one. We'll set it up as kind of two separate problems and then put them together. So let's do our heat gained first. All right. And then heat lost. And then I'll show you how we set them together. All right. So heat gain, actually, let's do heat lost first, just because the math is going to be a little bit more straightforward. All right. So who lost heat? Well, my 150 grams of water was at 75. And you're adding it to something colder. So that's going to be who lost right there. So I'm going to go, remember heat loss, so that's Q is equal to 150 grams. All right, and then my delta T, I'm starting at 75 degrees Celsius, right? And I want to figure out what will be my final temperature. I know this is losing heat. The final temperature is going to be less than 75 degrees. It's going to get colder. So I'm going to go, and just kind of for ease of looking at it, I'm going to take that degree Celsius away. So 75 minus X. All right. And then the specific heat, well, this is water. So specific heat of water is 4.18. So this is what lost heat. Well, what gained the heat? The 200 grams of water that was at 30. This is your cold water. All right, so for this case, my Q is going to be 200 grams. Now for my delta T, I started out at 30. This is going to get warmer. So X, that final temperature, is going to be higher than 30. So I'm going to set that up X minus 30, again, because we want that delta T to be a positive number. All right. And then times our specific heat. Okay. Because we know that the heat gained is going to be equal to the heat lost, we are going to set these two equal to each other. So let's go ahead. I'm going to rewrite it. 200 grams times X minus 30 is going to be equal to 150 grams times 75 minus X. Now, why did I get rid of the 4.18? Well, they divide out, all right? They're the same, so they divide out. I'm dealing with water in both cases, so I don't need to have that specific heat. If you were dealing with a mixture of two different things, that specific heat would have to be in there, okay? I'm going to go through and show the math for this. For some of you who just need a little review of your Algebra 1. If you don't need it, then feel free to kind of fast forward through. So I'm going to go ahead and distribute that 200 to the X and to the minus 30. So 200X minus 200 times 30. All right, so 200 times 30, and that's going to be 6,000. 6,000. And that's going to be equal to, I'm going to take this 150 and distribute it to the 75 and to the minus X. So 150 times 75 is 11,250 minus 150X. All right, you want to get your X's to one side. You want to get your values without the X to one side. So I'm going to add 150X to each side. So that's going to give me 350X is equal to, and then I'm going to add 6,000 to each side. All right, so, all right, so that's going to give me 17,250. You're going to divide, and I'm just going to scooch this up, make sure we're on screen. Divide each side by 350. Okay, and so divided by 350 equals, and you end up getting, for X, about 49.3. Remember, this was temperature, so degrees Celsius. And you should ask yourself, does that answer make sense? All right, remember we said that the answer must be between 75 and 30. Yes, absolutely, this is between 75 and 30. Now, feel free, if you like to do your algebra in a slightly different way, that's absolutely fine. I just wanted to go through that with everyone. All right, let's go on ahead and look at our last problem for today. All right, 25 grams of an unknown metal at 150 degrees Celsius is added to 50 grams of water at 25 degrees Celsius. The final temperature of the system is 39. All right, what is my specific heat? Okay, so let's go on ahead and take a look at this one, all right, because this is slightly different. So my heat lost is equal to heat gained. Okay, so who lost your heat? Well, your unknown metal, all right, was 150 degrees. You're adding it to something that's at 39. I'm sorry, it's going to end up going down to 39 degrees. It loses heat. So you have 25 grams of that unknown metal. All right, it started at 150 degrees and it went down, the final temperature of the system, to 39. We're looking for that metal, so it's the metal that lost the heat, it's the water that gained the heat. We're looking for that specific heat for that metal. Okay, well, who's gaining that heat? Well, it's the 50 grams of water. So I have 50 grams of water. It ended up at 39. It started at 25. Remember, we want to keep our delta T a positive number. And then the specific heat of water is 4.18. All right, you're going to do your math for that. And you should come up with your specific heat being about 1.06 joules per gram times degree Celsius. All right. Okay, fantastic, everybody. I hope everything was clear today. Please go on ahead and do the practice sheet and check your answers for the specific heat problems. Have a great day, everybody.